A clean energy solution? The potential of fusion power. Fusion reactors are designed to mimic the natural process of nuclear fusion that occurs in the Sun and other stars. In a fusion reaction, two atomic nuclei are brought together at extremely high temperatures and pressures to form a single, heavier nucleus. This process releases a large amount of energy, which can be harnessed to produce electricity. The most promising fusion reaction for energy production involves the isotopes of hydrogen, deuterium and tritium. These isotopes are readily available in seawater and can be extracted using a relatively simple process. When deuterium and tritium nuclei are fused together, they form a helium nucleus and a high-energy neutron, along with a large amount of energy. To initiate a fusion reaction, the deuterium and tritium must be heated to extremely high temperatures, typically in excess of 100 million degrees Celsius. At these temperatures, the hydrogen nuclei become plasma, which is a state of matter in which the electrons are separated from the nuclei. In order to confine the plasma and maintain the required temperatures and pressures, fusion reactors use magnetic fields or inertial confinement techniques. In magnetic confinement systems, the plasma is contained within a magnetic field, which prevents it from coming into contact with the walls of the reactor. In inertial confinement systems, the plasma is compressed using lasers or other high-energy sources. Once a fusion reaction is initiated, the energy released can be harnessed in a number of ways. One common approach is to use the energy to heat water or another working fluid, which then drives a turbine to generate electricity. Alternatively, the energy can be used to generate high-energy neutrons, which can be used for a variety of industrial applications. While fusion reactors have the potential to be a clean and virtually limitless source of energy, significant technical and economic challenges remain. Achieving the required temperatures and pressures for fusion reactions is extremely difficult, and the materials used in the reactors must be able to withstand the extreme conditions. Additionally, the cost of building and operating a fusion reactor is currently very high, although it is expected to decrease as technology advances and economies of scale are achieved. However, the development of a practical and commercially viable fusion reactor has been a major challenge for scientists and engineers. While significant progress has been made in recent years, a fusion reactor that can generate more energy than it consumes, known as net energy gain, has yet to be achieved on a consistent basis. The International Thermonuclear Experimental Reactor, ITER, and the Wendelstein 7X are two of the most prominent experimental fusion reactors in operation today. These reactors are designed to demonstrate the feasibility of a commercial fusion power plant, and they use different approaches to confine and heat the plasma required for fusion. ITER is a large tokamak reactor that is being built in Cadarache, France. The tokamak design uses a toroidal magnetic field to confine the plasma, which is contained in a vacuum vessel. The magnetic field is created by superconducting magnets, which are cooled to extremely low temperatures using liquid helium. The plasma is heated using a combination of radio frequency heating and neutral beam injection, which introduce high-energy particles into the plasma. One of the main goals of ITER is to achieve a net energy gain from fusion, meaning that the reactor produces more energy than it consumes. This is a critical milestone in the development of fusion power, as it is necessary for a commercial reactor to be economically viable. ITER is expected to achieve this milestone in the late 2020s or early 2030s. The Wendelstein 7X, located in Greifswald, Germany, uses a different approach to confine the plasma. This reactor uses a stellarator design, which produces a twisted magnetic field that traps the plasma. The magnetic field is created by a series of coils that are arranged in a complex three-dimensional pattern. The Wendelstein 7X uses microwave heating to heat the plasma, and it is designed to operate for long periods of time without interruption. This is important for commercial applications, as it would allow for more efficient operation and reduce the cost of electricity production. Both ITER and the Wendelstein 7X are expected to contribute significantly to our understanding of fusion power and the development of commercial fusion reactors. While significant challenges remain, the progress made by these experimental reactors represents a major step towards a sustainable and virtually limitless source of energy. Fusion reactors could offer a number of advantages over traditional fossil fuel power plants, including a virtually limitless supply of fuel, hydrogen, low greenhouse gas emissions, and improved safety. However, significant technical and economic challenges remain, and it is unclear when or if fusion power will become a major source of electricity.